Welcome back, everyone. This is the last course of this Python specializations for deep learning in TensorFlow. So far, we've covered the most commonly used types of neural network and learned how to implement them with the use of TensorFlow Keras, and specifically with the use of the sequential models. But sometimes we might want to build some more complex architectures that sequential models cannot fit in. And in that case, we will need to use another TensorFlow Keras functions, namely functional API, to construct those types of models. In this final course, we will explain what kind of architectures that we need to use functional API, and we'll have a chance to build a new models with the use of the functional API. After having some understandings about the functional API, we will then learn some specific features of the API. For example, how we can use a part of the complete architectures to define different types of the models, and how we can manipulate the complex graph topologies, and how we can share the layers, and how we can extract and reuse a node from the architecture. There are lots of things to learn, so let's go ahead and get started. Let's refresh our memory a bit. Keras is a simple tool for constructing a neural network. It is a high-level API of the TensorFlow tool. So far, we've used the TensorFlow's 2-point-somethings to implement the Keras. That is an approachable, highly productive interface for solving machine learning problems and focusing on deep learning. The core data structure of the Keras are layers and models. And of course, just like what I mentioned, there are two types of models. The simplest one is the sequential models, which is a kind of like a linear stacking of those layers by layers. And for more complex architectures, the Keras functional API that has to be used in order for us to build a graph of the layers or write the models entirely from scratch. The Keras functional API is a way to create the models that are much more flexible than the sequential API. The functional API can handle models with nonlinear topology, shared layers, or even multiple inputs and multiple outputs. Say, for example, this is the multiple input. We have the text image, we have the input, we have the image, we have the text input, we have the image input, and then we try to combine these two inputs as the multiple inputs together with a concatenate layers, and then to predict the outputs. This is the multiple inputs. On the other hand, this is the multiple output topology. Say, for example, one of the results that we would like to use the classifications, and the other types of the results that we would like to have the regressions. So in that case, we have the predictions with the probability. At the same time, we have, say, certain types of predicted value. And then finally is that sometimes we might want to share the layers, or we want to skip one of the layers at some point. And in that case, we can also use these types of functional API. So the main idea is that deep learning models is quite complicated at some point, at some times. In that case, we need to use the Keras functional API. And therefore, the functional API is a way to build a complex graph of layers. Now, let's take a look to see how we can build a neural network with the functional API before we dive into different types of topologies. This exercise try to train a neural network to classify image of clothing like sneakers and shirts that we come across before, But before we use these sequential models, but at this point, we will, at this exercise, we would like to use the functional APIs to build such model. First thing first, of course, we need to import the Keras, we need to import the layers, and also, of course, we need to import the TensorFlow, because we are going to have some kind of calculations. We need to import NumPy, and for visualizations, we are going to import the matplotlib. Let's run this out. This is the fashions MNIST models. This is the models that are slightly more challenged than the classic MNIST. For this one, it contains 70,000 grayscale image in 10 categories, as shown here. Say, for example, 0, label 0 represent the t-shirt, and so and so. Each example is a 28 by 28 grayscale image. This is what it looks like. The fractional MNIST data can be imported and loaded directly from the TensorFlow. The dataset contains 60,000 image of the 10 fractions categories, along with the testing image that contains the 10,000. So 60,000 is for training and 10,000 that is for testing. And we'll later on to have a look on this shape. So the training image is a number array that has a shape with a shape 60,000 20x by 20x. That is the training image, and their corresponding training labels is a 60,000 vectors that contains the integers ranging 0 to 9. And the testing image is a 10,000 image that contains 10,000 image, and the testing labels has a 10,000 corresponding vector. So we can just load the fashions MNIST. And at the same time, we also, because everything has been stored in a 20x by 20x number weight with pixel ranging from 0 to 225, we also would like to create a list to represent the class names. So what we're going to do is to create this class name list. And let's explore a bit of the data. This is the shapes of the data. This is the shapes of the this is the shapes of the training data, and this is the shapes of the testing data. So you can see that the shapes of the training image is 60,000 20x by 20x, and then the corresponding label is 60,000, and so and so. And for the labels value, let's take a look on that. That is the range from 0 to 9. This is their corresponding class name. And finally, let's take a look on the pixel and also the picture. The pixel value range from 0 to 255, and these are the picture. In that case, we also would like to normalize the data, because the data normalization is usually used in machine learnings to make the models less sensitive to the scales of the features, and it allows the models to converge faster. So what we're going to do is to normalize the trainings and also testing sets. And after the normalizations, you can now see the pixel range now is range from 0 to 1 instead of 0 to 255. And just like what I mentioned, they are in grayscale. Now we are ready to build the model. Let's consider this as a flow chart of the models that we wanted to build. We are going to have an input image that is 20x by 28. And the first things that we would like to do is to flatten the image to a vector, before it allows us to put those things into the TensorFlow into the neural network. So after flattening these image, we will then have a dense layers that contains the 120x units with the value activation functions. And after learning the features, after learning some features from the image, we will then have another output layers that is a dense layers with 10 units with a softmax activation functions, and the output is a logics of the probability distribution over the 10 classes. Okay, so now let's set up and configure a functional API models corresponding to this graph. The first thing what we're going to do is to have the input that is the Keras input, and the shape is 20x by 28, and it will be assigned equals to the input. So let's run this out, and now these inputs is returned, and it contains the information about the shape and also about the types of the input data that we fit into the model. So this is the shape. None means that that is the batch size. We do not define at this point. It allows more flexibility. So we do not need to determine the number of sample, but of course we need to determine the shape and the types of these input layers. Of course, this is the TensorFlow float layer. To add layer is like drawing an arrow from the inputs to the layers that we create. We are passing the inputs to the dense layer, and what we're going to do is we get X as the output. So what we're going to do is that we first define the layers. The layer is layers.flatten. And then we're going to provide the input, and the input is these inputs. So what we're going to provide is these inputs as an argument. So we have the layers, we have the inputs, and what we're going to do is to assign x1 as the output. So just like what we have here, the inputs, the flattened layers, and then the output. Similarly, we can then add another layers to the graph of the layers. And for these times, we're taking out the input, we're taking out the output from the previous layer, that is x1, that is the output x1 from the previous layer. We are going to construct a layers that have that is a dense layer, have 128 units with the value activation functions. So we create the layers dot dense 122 and 28 units, and then the activations value function. So we have the input x1 from the previous layer, and then we have the output x2 from this layer. Similarly, let me run this out and this out. Similarly, we can add another layers to the graph, and this is the final layers. So that is the layers.dense with the 10 units softmax, and then the output is x2 from the previous layer, and of course the output is the output. At this point, we just create the inputs and outputs in the graph of the layers. Now we need to put everything inside a model. And now, so this is the Keras models. The arguments is the inputs equals to the inputs, that is the inputs that we have over here, and output equals to the output, that is the output over here. And of course, we've already created some graph in order for us to create to predict this output. Now, of course, we can also provide a name for this model. And finally, we assign everything to equals to the model objects. The architecture is like this. So we have the input that is 20x by 20x, and then we flatten this out. We flatten these outputs layers, and then we provide these vectors into the dense layer, which has 120x units, and that is a value activations function with the value activation functions. And finally, of course, we have the outputs layer that will take these inputs take these output shapes as the inputs for these layers. And finally, it will return a 10th output that corresponding to the 10th classifications. And we can also plot the model as a graph. So we have the inputs layer, we have the flattened layer, we have then two dense layers that provides the output. For the setups to how to use these utils plot models, please feel free to refer to the appendix at the bottom. And of course, we can also display the input and output shapes for each of the layers plotted in the graph. This provides you much more detailed information because it contains the input and output shapes. So in that case, sometimes it's much more useful to make sure that we create the models that we want. And the next thing, of course, we can compile the models. We're going to use the optimizer atoms, and we're going to use the loss functions, that is the sparse categorical cost entropy. And because we've already defined the activation functions at the outputs layers, from logics, we can set it as false. And then for the metrics, we use the accuracy as the metrics. Just like what I mentioned before in the previous course, because we are not using one-hot representations, we are using the labels as the integers. So we're going to use the sparse categorical cost entropy. And let me run this cell to compile the models. And then finally, we are ready to train the models. So everything here is exactly the same ways for building the models that with the use of the sequential models that we previously used. So for the functional API, everything is the same. So we just use the model.fit and then train the image that is normalized with the training labels and epoch equals to 10. Now we can fit and train the model. Now the training has completed, and after 10 epoch, the accuracy, which around 91%, the model is not bad for evaluating these fashion amyloids. And of course, we can also evaluate the models. It turns out that the accuracy is around 87%, which is quite close to this accuracy. However, the gaps might be because of the overfitting issue. So now let's verify and also visualize the predictions. Let's predict 16 image. And against the correct predictions, labels are blue, and the incorrect predictions, labels are red. And let's see how much that we get in this, how much correct image that we correctly predict. So we, most of them are correct, except that we have a run incorrect predictions. That is this one. That is actually a sneaker. So just like what we mentioned before, even it has a very high confidence in the predictions, sometimes it's still incorrect. So we have to be careful at this point. And finally, we can also use the models to make some predictions. So say, for example, we pick one of the image that is from the testing image. So this is the shapes of that image that is 20x by 28. Remember that when we are training the models, we use a batch of the same examples to train up the models. So in that case, in order for us to predict the output from this image, we need to insert a new axis that will expand in the array shaped. So for this case, we just consider it as one sample or one sample in those batch. So now we are ready to put this image into the models for predictions. And for this case, we're going to use the .predict functions and put in the image. And now we can see what it predicts. The highest confidence is 4, and the predicted class is code. Let's see if we predict it correctly. Yep, perfect. The models predicts the labels correctly. And that's it for these lessons. We have briefly introduced the functional API and learned how to use the functional APIs to construct a simple neural network for predicting image. Now we have a better understanding about the functional API. In the next lessons, we'll dive into some important features of the functional API. So see you in the next video. Bye-bye.